A slight shift in retail consumer demand rarely stays localized. As it travels upstream, it mathematically amplifies into massive, chaotic inventory disruptions. Supply chain architects call this the bullwhip effect. It is a structural vulnerability that paralyzes working capital by forcing organizations into an alternating cycle: severe stockouts when demand spikes, followed by massive overstocking when orders are aggressively corrected. Historically, departments operated in absolute silos. Demand planners blindly guessed future sales, while procurement teams separately purchased materials, hunting for the cheapest sticker price. In today's landscape of extreme market volatility and geopolitical shocks, this reactive, disconnected model fails to meet the speed of global demand. To see the solution in practice, we have to look at the high-tech manufacturing ecosystem of the Free Trade Zone in Batam, Indonesia. This region serves as a real-world laboratory where legacy supply chain models were being actively dismantled. Building a resilient, modern supply chain here requires uniting two complex systems. First, the organization must generate high-fidelity demand signals using artificial intelligence. Second, procurement teams must execute the buy based entirely on total cost of ownership. Batam's industrial leaders prioritize mathematical precision across the end-to-end architecture over the traditional reliance on massive safety stock buffers. We begin at the first node of the supply chain network, generating the demand forecast. Every downstream action depends on the accuracy of this single projection. For decades, analysts relied on baseline forecasting methodologies, like the simple moving average and exponential smoothing. The fatal flaw of these time series methods is that they are linear equations. They attempt to predict future market behavior purely by extrapolating from historical sales data. This graph illustrates exactly why these traditional models collapse during sudden macroeconomic shifts or unprecedented events. The solid line representing actual demand spikes and drops erratically, while the moving average projection lags entirely behind, missing every critical market shift. To eliminate this lag, operations managers are shifting to machine learning, specifically deploying long short-term memory, or LSTM, neural networks. Rather than relying on historical spreadsheets, artificial intelligence processes real-time, unstructured, high-dimensional big data aggregated from thousands of global sources. The algorithms scan these massive datasets for latent correlations human analysts cannot see, like identifying a pattern of blank sailings and delayed vessels at major shipping transit hubs, to predict an impending component shortage weeks before it hits the factory floor. These same networks simultaneously factor in consumer sentiment from web searches and track real-time commodity index fluctuations to constantly calibrate the forecast. Take a smart home appliance manufacturer operating in FTZ Batam. Facing extreme volatility, they ran a side-by-side test on a production run of microchips. To evaluate performance, logistics managers measure the absolute percentage error, or APE, comparing the traditional moving average against the machine learning model. Look at this split-screen visualization of the results. The traditional moving average method yielded a disastrous 20% forecasting error. The machine learning architecture successfully absorbed the market volatility and dropped that error rate down to just 2%. Dropping the error rate by 18% solves a massive physical problem. It frees up millions in working capital that previously had to be trapped in warehouses as useless safety stock just to buffer against inaccurate guesses. Once the neural network generates a precise demand signal, the procurement team must execute the buy. A common misconception among amateur purchasers is that securing the lowest initial unit price is the primary measure of success. Professional sourcing managers reject this. Instead, they use a financial framework known as total cost of ownership, or TCO, calculating the complete life cycle expense of the material. We can see how this works through a real-world scenario at PT Schneider Electric Batam. The purchasing department needs 100,000 integrated circuits and must choose between two distinct suppliers. We can see the unit price fallacy in action on this TCO waterfall chart. Supplier A takes a reactive approach and offers a highly attractive unit price of 10,000 rupiah. Supplier B acts as a strategic partner. Their initial unit price is noticeably more expensive, coming in at 10,500 rupiah, but the baseline price is only the beginning. Supplier A refuses to collaborate on engineering. This results in a 5% defect rate on the assembly line, immediately adding 10 million rupiah in quality replacement costs. Furthermore, supplier A lacks just-in-time integration. The factory has to hoard excess inventory to prevent stockouts, piling on another 50 million rupiah in warehouse holding costs. Now look at the hidden costs for supplier B. They utilize quality value engineering to refine the material mix. This drops the defect rate to 0.5%, costing a negligible 1 million rupiah in replacements. Supplier B also calibrates their deliveries to perfectly match the factory's just-in-time schedule, drastically shrinking holding costs to a mere 10 million rupiah. When we calculate the final total cost of ownership, the math is undeniable. Despite charging a higher initial sticker price, supplier B is ultimately 4 million rupiah cheaper to operate. By optimizing the full lifecycle cost, strategic sourcing generates measurable profit for the corporation. This raises an operational question. How do managers objectively identify a premium partner like supplier B before signing a massive contract? Supplier evaluation is classified as a multi-criteria decision-making problem. Variables like component quality, delivery reliability, and unit price often directly conflict with each other. To resolve this, supply chain architects use a mathematical methodology called the Analytical Hierarchy Process, or AHP. Batam Aerotechnic relies on AHP to navigate the highly regulated aviation maintenance, repair, and overhaul sector. This hierarchical decision tree breaks down the math they use to source aviation paint. The managers assign specific operational weights to each metric. Quality is heavily weighted at 0.51, reliability sits at 0.24, and price is given a low weight of 0.12. This mathematical weighting system actively prevents human purchasing bias from accidentally prioritizing the cheapest bid over technical integrity. When sourcing materials bound by strict Federal Aviation Administration safety regulations, mathematically prioritizing quality prevents catastrophic operational failures and legal penalties. To function properly, the entire supply chain architecture must operate as a closed, interconnected feedback loop rather than a series of isolated nodes. The ultimate standard for this organizational integration is known as Collaborative Planning, Forecasting, and Replenishment, or CPFR. CPFR creates a truly unified data environment. It connects the artificial intelligence's cloud-based demand signal directly to the physical operational speeds of the machinery on the factory floor. This synchronicity is mandatory when manufacturing highly advanced, defect-sensitive components, such as smart AR prisms or specialized medical lenses. But there is a final physical reality check that predictive algorithms cannot override: absolute capacity constraints. At PT McDermott, a corporation building massive offshore oil rigs, managers constantly monitor their subcontractors' capacity utilization rate. It is quite literally a matter of life and death. If procurement floods a welding subcontractor with orders that push them past their safe maximum operational limit, the physical integrity of the welds degrades. That direct drop in quality invites an offshore structural disaster. To prevent this overload, the system relies on a mathematical governor known as the Economic Order Quantity, or EOQ. This EOQ chart illustrates how managers calculate the exact optimal order size. It identifies the perfect equilibrium, the lowest intersection point on the total cost curve, where ordering costs and warehouse holding costs meet. By adhering to the EOQ, the architecture dictates a precise, sustainable cadence for material flow. Suppliers are never operationally overwhelmed, and factory warehouses are never bloated with excess stock. The modern supply chain functions as a disciplined ecosystem of predictive algorithms and holistic cost models. In this environment, actionable data provides a more significant competitive edge than physical inventory.